Hello everyone, John CFG here, and before we get started in today's video, I want to give a quick disclaimer as always. Despite my YouTube username being John Teacher, I am not a real teacher. Instead, I am a student of computer science willing to work through a couple of practice problems. And today's topic is CFGs, or in other words, context-free grammars. So, without further ado, let's get started on the first problem. So, first problem is going to be the language of a to the I b to the I, c to the j, such that I comma j is greater than or equal to 0. So in sort of these, I don't know how to explain it. Counting CFG problems is going to be the common theme of what we're going to do today. I want to highlight a couple things. If you remember, CFGs, kind of the way that they're structured is you have a start and then you have anything to the left and anything to the right. And so that's kind of the mindset I want you to think about going on. So we have our start like this. Maybe we could have something like that, like double, or it's inside the entire thing, and we have a start like this. So kind of thinking things as sort of groups is going to really help, is what I'm trying to highlight. And first thing we notice in this practice problem, A and B to the I, C to the J. So we could sort of kind of formulate these as groups. And another thing we have to pay attention to is that A to the I, B to the I. So that means that however many number of A's there are, there should be that exact number of B's. So as always, we're going to start with our variable. Okay, let's sort of take this and just write it how we normally would for A to the I, or A to the I, B to the I. Okay, so S goes to A, S, B, or epsilon, right? That would sort of define our group right here. Okay, now let's think of C to the J. S would go to C, S, or epsilon. Okay, so now we kind of have to bring these groups together. Okay, and what will we get? Well, if we're going to bring them both together, a way we could do this is by splitting up the work into x and y. Okay, so x goes to A, S, B, or epsilon. Okay, and y goes to C, S, or epsilon. Okay, so a and b to the I greater than or equal to 0. Well, it could be epsilon, it could be ab. Okay, let's just check this x rule. So s goes to xy, and the x right here could be epsilon, ab, aabb, dot, dot, dot. All right, and then the y right here can be epsilon, could be c, could be cc, and it keeps going. So yeah, and the xy, they concatenate both of them together, so it would be AA, BB, CC if we combine the last two. And yeah, that is going to be the language for the context-free grammars, such that A to the I, B to the I, C to the J, such that IJ is greater than or equal to 0. Let's move on to the second problem. All right, for the second problem, we're going to be thinking of the language. Oop, sorry. The language such that, go away. A to the I, uh, B to the J, C to the I, such that I comma J is greater than or equal to 0. Sorry about that delay. I wrote the problems in advance, but my handwriting on this one was a little questionable. And as always, I think I forgot to mention it before the first problem. I highly recommend when I write the problem, pause it, work through it, hit play on the video. You know, it's just a better way of practicing than to watch somebody doing it because you firsthand witness like gaps in your understanding that you may not realize just watching me by doing it. So, all right, let's highlight this problem. We're going to notice that these two are in a group together with B in the middle. That is a little weird, so we're not going to be able to sort of split it up into this XY like we did before. And I should have boxed that solution in to make it a little more clear. But, so yeah, we can't split it up like this. However, we could think of it in terms of S, right? So a bunch of A's, dot, 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 S, B, B, B. And in this middle part, maybe we could switch it to a different variable. B, 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 and then in that variable X, we could put a bunch of C's. Okay? So we build the left side, we build the right side with a bunch of A's and C's. Or, oh God, these should be C's. And these should be B's. All right. Sorry about if that caused any misunderstandings. But if we build the left side with A's, the right side with C's, okay? We finish that up, and then we sort of build our inner layer, kind of like we're sandwiching the B's in, okay? So S can go to A, S, C, or epsilon. Not quite. Instead, we're going to think of our terminating case as X, and then X would be all of our B's. Okay, let's think about it. S, A, S, C, A, S, C, C, and then maybe it gets replaced with an X, A, X, C, C, and then we have A, B, X, C, C. Don't want it to be capital C's. Oop. Don't want it to be capital C's. Okay, A, B, C, C. Okay, I and J can be greater than or equal to 0. Well, yes, they can. S could just go straight to X, or yeah, S can go straight to X, and then X could just straight go to epsilon. All right, this is going to be the context-free language. For languages A to the I, B to the J, C to the I, such that I and J are greater than or equal to 0. All right, let's move on to our third problem of today. It is going to be the language of A to the I, B to the J, such that, or not A, I is greater than J. Okay, couple things to clarify. When I say I is greater than J, and we can't have, I don't know, negative characters in this world, um, at least to my understanding, can't have negative characters to this world. You never know. But the least something can be is 0, and if I is strictly greater than 0, that means I is greater than or equal to 1. So let's just clarify that. And J is greater than 0, and I is greater than J. Because if I is greater than J and J is 0, I cannot be 0. So the least count of I we could have is 1. The least count of I, or the least count of J is 1. Or 0, I mean. Okay? Keep this in mind. So this one's a little bit strange because I must be greater than J. So we need to keep track of that somehow. They're going to be right next to each other. So that's a common standing point. We're going to have to slap them in like this, right? Okay, but if we do epsilon, the number of i's and j's are going to be equal, right? So we're going to need another variable handling the extra behavior. But something I want to highlight here is notice, I believe we did palindromes in part 1. This would create a even length palindrome if x was epsilon. Okay, this would. And so at this point, what this is saying right here, leading up to this x call, is that there's an even number of a's and b's. Now we just need to ensure that there can be a greater number of a's. That doesn't mean there's like just one more a. There could be an infinite amount of more a's. There could be 10 more a's, 100 more a's, 1,000 more a's. Okay, so now x has to cover this case where I is greater than j because a to the I, b to the j. Okay, a to the x or epsilon. Seems good to me. Is that our final answer? There's one small caveat. I want you to think about it. Well, let's think this through. We take S, we go A, S, B, we go A, S, B, B, and then we go A, X, B, B, and then we go A, epsilon, B, B, which gives A, B, B. Well, the number of A's isn't greater than the number of B's. How can we fix that? Well, this call to X right here, I left a little room right there because we're going to put an A. We need to ensure that there's at least one more A than a number of B's. And we have ensured this, so that is our solution to the language of A to the I, B to the J, such that I is greater than J, or there's more A's than B's. All right, last problem of today is going to be the language of A to the I, B to the J, C to the K, such that I, comma J, comma K is greater than or equal to 0, and I equals J, or J equals K. Now this is an interesting case. We have an or right here. So the number of i's equals the number of j's, or the number of j's equals the number of k's. Same number of a's and same number of b's, or same number of b's and same number of c's. Okay, interesting. So before we even start by writing this out, it's a bit of a more complicated one, I will admit. But let's think this through. We have an or. Well, what can we do with an or? So we have option 1 or option 2. Well, that's a good way to think about it. So let's start with our start variable. We have option 1 and option 2. Now, for those of you watching along, this is a really big hint to get this working, to get this sort of started. So think of U as path 1, V as path 2, and try to work from here. Okay, let's continue. So what do I mean by option 1, option 2? Well, this can be option 1. I murdered that there. Oops, I'm sorry. Option 1, option 2. Okay, option 1 and option 2. So let's take the path of option 1 for you. In option 1, the number of i's is equal to the number of j's. Okay, which is basically the equivalent of saying a to the I, b to the I, c to the k. And option 2 would be a to the I, b to the k, c to the k. Okay, that'd be roughly the same thing. Could switch the variables around. But option 1, a to the I, b to the I, c to the k. Okay, we sort of see these natural groups start to form. Okay, so we have A, and this is very similar to problem 1, which, other than the change K. We have sort of the starting group, another group. Let's split up the work. Let's name it A. How do I want to name this? We could do A subscript 1, B subscript 1. Okay. So in the A's, what we're going to do, don't know why you were here. In the A's, what we're going to do, A subscript 1, sorry, we're going to go to A, S, B, and this is going to build the left side of our problem. Okay, so we have A, S, B, and then we either go to epsilon, and then B subscript 1 is going to go to C, B subscript 1. I wrote S. I meant A. I apologize. And then, or epsilon. Okay, so this is going to, is going to cover option 1. Now, option 2 is going to be really similar. We're going to have V goes to A subscript 2, B subscript 2. So A subscript 2, and then we have B subscript 2. And this time it's going to be B and C to the K, and then A to the I. So A2 is going to go to B to the K and C to the K. Not quite. They're on the right. And A2 is on the left. So A2 is going to be containing the A's. So A2, or epsilon, and then B is going to contain B, B2, C, or epsilon. This is going to cover option 2. Another mistake that, I don't know, at least I commonly tend to make, which is why I made it here, is notice how I put UV on the top, concatenated. We need to pay special attention to the fact it's U or V. We're choosing the paths. We're not concatenating them. I don't remember if I made this mistake on a quiz. I want to say I made this mistake on a quiz. That's why I feel like I highlighted it. I wanted to highlight it here. But yeah, another big takeaway. You might even be like, hey, we could add epsilon here. I'd argue it's not necessary because all our cases right here already handle the epsilon. You could add it. It would be redundant. Not the end of the world. So this is going to be the language such that A to the I, B to the J, C to the K, such that I, J, K greater than or equal to 0, and I equals J or J equals K, which I don't know. You could always read comments as sort of and if I've never mentioned it before. That's how I kind of read them. But yes. And that is it for today's video. Thanks for watching.